Hello and welcome to this talk. In this presentation, I want to talk about benchmarking and improving static data flow analysis on binary executables. First of all, we want to know why data flow analysis is important. Data flow helps us to track how data moves through a program, and it's already a hard problem at source level. But at binary level, it's a much harder problem due to loss of high-level semantic information during compilation. As a result, in this research, we want to evaluate how existing approaches can detect data flows at binary level. In this research, we first propose a taxonomy and different categories of data flows at binary level, and then we propose a synthetic microbenchmark that can be used for static data flow analysis evaluation. And then we evaluate three famous open source tools such as angr, Ghidra, and Miasm on our generated microbenchmarks and on some real-world programs. Then we propose three extensions and improvements over angr. And at the end, we verify three case studies on vulnerability discovery and show how data flow improvement can help to discover real-world vulnerabilities. First of all, we want to introduce a taxonomy of data flows. First of all, I have to mention that in this research, we only focus on intra-procedural data flow analysis. And our goal is to determine whether two instructions, memory write and read from memory, has a data flow, and they access the same data. In this research, we propose four different categories and four alias classes for data flows: stack, heap, global, and foreign. Foreign means that a pointer that is defined outside of the function and it is introduced using function argument. And global is allocated upon program initialization and accessed using constant address. A stack is accessed using offsets from stack pointer, and heap is introduced via the return value of a memory allocation function. Since we want to evaluate the data flow between memory write instruction and memory read instruction, and for each instruction we have four different categories and alias classes of data flows such as stack, heap, foreign, and global. If we multiply these two categories at the end, we will have 16 alias classes, and for each alias class we can define three different data flow degrees: unconditional data flow, possible data flow, and impossible data flow. Unconditional data flow means that on every execution of the program in which these instructions are executed in order, there is a data flow from the memory write and memory read instructions. You can see such example in this slide. Possible data flow means that at least one execution of the program, on one execution of the program, there is a data flow from the first instruction to the second instruction. As you can see in this example, if RSI register is equal to 0, then there is a data flow between the first and second instructions. Impossible data flow means that on every execution of the program, there is no data flow from the first to the second instruction. As you can see in this example, RDI can never be equal to RDI minus 8. We created a synthetic microbenchmark in order to evaluate existing open source approaches for data flow analysis. With respect to different classes and alias classes of data flows, and also different degrees of data flows, such as unconditional, possible, impossible, and also different data types and array allocation lengths, and by considering calling interruptions and different compiler options, we mix all these parameters together to create a synthetic macro benchmark, and that results to 200,000 target binaries. We use these binaries in order to evaluate three tools. We evaluate angr, Ghidra, and Miasm on our created synthetic macro benchmark, and for different categories of data flows, and also for different degrees, such as impossible and unconditional data flows. And as you can see, in all cases, angr reports lots of impossible data flows, and it means that it has a high false positive. Then we evaluate these three tools on open source projects, and this is a list of projects that we used in order to establish the ground truth for the real world binaries. We use dynamic analysis and we use PIN framework to do that. And since dynamic analysis is not complete, we only evaluate these three tools on the ground truth that we could establish during dynamic analysis. And as you can see in this figure, angr still has imperfect recall in practice. So we investigate the reasons and the philosophy behind the limitations of angr in order to propose some extensions and improvement over angr, and we came up with three extensions over angr. Just to remind that in this research, we only focus on intra-procedural analysis. angr, in this case, whenever we have a call function between a memory write and memory read instructions, regardless of what register is used, angr will always kills the data flow, because we really don't know what call function does, and if the call function modifies the value in memory or not. On the other hand, with respect to calling convention, which specifies which registers are used to pass function arguments, unlike angr, whenever we have a call function, we assume that there is a data flow between memory write and memory read instructions. And in this, this research shows that in practice, it can produce, it can improve the results. Our second extension is about a specific case when we use RSP register as a register to be used for writing to a memory or reading from memory. And we know that whenever we call a call function, the RSP register will for sure be decreased, and angr in this case will kill the data flow between the gray and green lines. But in our extension, we assume that because the call function, when we call the call function, it will decrease the RSP, but when it returns, it will increment the RSP. So in this case, it seems that nothing has happened, and when we return from the function, RSP will has the same value as before, and so we can say that there is a data flow between the gray and green line. Our last extension is that whenever we have an unknown address, the angr strategy is to replace that unknown address. For example, when it comes from outside of the function, it will replace it with a fixed value. Angr in this case will replace the gray and green line with the same fixed value, and as a result, it will report that there is a data flow between the gray and green line. But in our extension, with respect to constant offset, we believe that RDI and RDI plus 8 are not equal, and there is no data flow between the gray and green line, and in this case we can improve the data flow performance. As you can see here, this is the this is the result of angr CF, which is our extension over the angr on real world binaries that were compiled by GCC and Clang, and you can see that the precision recall and F1 score metrics were much higher than the original angr. Then we used, our extension angr CF for on some vulnerable functions. For example, in this case, we had an integer overflow on OpenJPEG2, and we showed that our extension can help to retrieve the relevant lines of code that is related to vulnerability. For example, at the left side, you can see that the highlighted lines are related to vulnerability, and whenever we have a callee function, for example here we have getC, angr will kill the data flow between these lines, while our strategy is to keep the data flow, and you can see that in this case we can detect 12 true positives that were missing by the original angr. And this is the same story for the second case study. You can see that the highlighted lines are have a data flow with each other, and angr, because we have memcpy, it will kill the data flow. But in our case, we could find 36 true positives that were missing by the original angr. And the same story for a buffer overflow, that data flow was killed by a callee function, while we could retrieve and find 27 more true positives. So as a conclusion, our evaluation of angr, Ghidra, and Miasm reveals that there is a substantial limitation in binary data flow analysis, and they have a high false positive and false negative rates. And as a result, we introduced 3 novel extensions to improve data flow analysis, and our extensions significantly improve the recovery of relevant binary data flows and vulnerability-related information.